All right, welcome everyone. Let's begin. Any more submissions for the homework assignment? Homework 8? I'll give you the next homework assignment when we get together in class on Tuesday. That'll be homework number 9. And it's going to be building on in-class exercise we do together today. It's called the Streeter-Phelps Lake Quality Model. River model, and then we're also going to be talking about lake quality in future classes as well. Also, as a reminder, the research paper initial submission is getting closer. The deadline for that will be on Thursday the 12th. You're welcome to stop by my office during the office hours if you want to show me what you've got along the way, but that draft submission will be uploaded to iLearn. You guys can collect those papers after class. You don't have to do it right now necessarily. All right, so will you please close the door? What we're going to be talking about today is BOD breakdown. I apologize that there's no class notes. They still haven't fixed the printing machine over in the main building, so I sent a reminder email. I'll post, the slides are actually already uploaded onto iLearn, and I did print only a couple of the in-class exercise handouts, so I'll ask you to double up when we get to the point where we start working on those. You'll have to share them, and then I'll post the solution online. What is BOD? No, that's what it stands for. What is it? It stands, the acronym is an abbreviation for biochemical oxygen demand, but what is biochemical oxygen demand? Good, very good. So it's the amount of oxygen that's going to be used in the breakdown of a waste. And so it's an indirect measure of how much waste is there, because we know that the oxygen demand is really the issue that we're worried about because of the impact that's going to have on the aquatic life. So we've seen this slide before, that there's a sag and the initial amount of dissolved oxygen is going down. It reaches a critical point, and then it starts going up again. Why is it going down here? It's because the bacteria are consuming BOD, and they're also consuming dissolved oxygen. And then the dissolved oxygen starts to go up again. For what reason? Right. The reoxygenation is just that there's air in the atmosphere, and here the water is touching the air, and so there's transfer from the oxygen in the air to the oxygen in the water. What we're going to be looking at today is what happens in a river that's flowing downstream. And the big idea that we're going to be using in this analysis is that idea of a deficit, dissolved oxygen deficit. And so the deficit is how far below the saturation dissolved oxygen you are. So imagine that this dissolved oxygen line continued onward, and we're measuring the distance between where the dissolved oxygen is and where it should be. That's the definition of deficit, is the difference between the saturation concentration of oxygen and the actual oxygen concentration at a certain point. As a reminder, oxygen re-enters through the air, and so that's why we see this deficit getting smaller over time, but it's a very slow process. And usually, the resupply of oxygen back into the water is a much longer curve than how long it takes for the bacteria to cause the dissolved oxygen to drop. And so what we're going to be doing is looking for a model that explains how big is this deficit going to get, because we want to know, is it going to get low enough, is the dissolved oxygen going to go low enough that it starts to harm aquatic life, that it starts to kill fish, and also if it starts to cause the production of methane directly from the water itself, because if the dissolved oxygen gets low enough, then it can cause the waste to begin breaking down anaerobically. So we want to know, where is the dissolved oxygen level in the stream at every point in the stream. The way that we do that modeling is by looking at rate constants for how quickly the water is being consumed, and that's what we call a deoxygenation rate constant. And so oxygen consumption is one constant that we can look at, and then the resupply is another. Both of those relationships are first order, and so that the resupply depends on the difference between saturation and what is there, and so the amount is an important factor in both resupply, and the amount of how much oxygen there is depends on how quickly it's being used. So you can see that the further away you get from this line, the more quickly it's resupplying. And so this deficit, when the deficit gets small, the reason why the curve is starting to flatten out at this point is because the distance between the saturation curve and the concentration curve is getting smaller and smaller. And so the smaller the difference, the slower the resupply. If we do a mass balance on a single element of water that's in the river, what we could look at is the rate of accumulation of how much oxygen is there inside of this little element of water as it flows down the river. And we're going to look at the difference between how much is going in, how much is going out, if there's any oxygen production inside of this element of water, and the consumption of oxygen inside of that water. This is the basic ideas of the Reynolds transport theorem, that we can do a mass balance on any particular anything, and we can keep track of the mass flowing in and out, and then know if there's an accumulation, and then the opposite of accumulation is a decrease in how much oxygen is in there at a particular time. Let's make an assumption just to simplify things for ourselves. Let's assume that inside the river there's not any oxygen that's being produced. Now sometimes in a lake, algae can produce a little bit of dissolved oxygen if there's enough algae. And the dissolved oxygen that they produce would be a small fraction compared to the amount of oxygen that is transferred in through the atmosphere. So let's assume that there's no production of oxygen inside of there, and let's also assume that the bacteria are consuming oxygen, but there isn't any loss of oxygen, like the oxygen isn't going out of the water and into the air. And that's a pretty good assumption as well. So if we simplify our overall mass balance and say that oxygen is going in and oxygen is being consumed, but these other two terms we cancel out just to make our modeling easier. So we say that the change in how much oxygen is there is just the difference between how much oxygen is coming in and how quickly it's being consumed. And so what we have to do is we have to have an equation that will account and factor for both of these things. How quickly the air is getting back in and how quickly the bacteria are using the air. Any questions so far? All right, as I mentioned, both of these equations are first order. And so deoxygenation is just the rate constant that we can either estimate with an empirical equation, or sometimes we can look it up off of an empirical table. And then the difference between how much BOD is initially present and how much BOD is present at a certain time. And this is, this difference here, this driving force, is how much food remains for the bacteria to consume. So if they have a lot of food, then we can just infer from that that they're also going to be using their oxygen very quickly. They're using their substrate, which is a fancy word for food. They're also using their oxygen. Now for reoxygenation, there's also a difference here, a driving force. And the driving force is how far away you are from saturation. So if you're very far from saturation, that means the oxygen is going to be coming back into the river very quickly. But if you're very close to saturation concentration inside of the river, then the rate of reoxygenation is slower. And how quickly the oxygen can get back into the water also depends on whether there is a slow-moving water or if it's moving quickly. Because as you'd expect, a water that's moving very fast and has lots of rapids and turbulence will have more contact with the atmosphere than a slow-moving river that maybe is deep and stagnant water, so the gas transfer would be slower. Here's just an example of a couple of empirical equations that can be used to estimate both the deoxygenation rate constant and the reoxygenation rate constant. Of these, in the homework assignment that I'm going to give you on Tuesday, I'll have you only use the reoxygenation rate constant. You can see it's a function of both the velocity of the water, the depth, and also the temperature of the water are the factors that are accounted for in this equation. Here are some tables that estimate reoxygenation, and these different categories are different types of streams depending on how quickly the water's moving. So a small backwater would be very slow-moving water, and then you can see as we go down through the list, swift streams, then rapids, and the reoxygenation rate constants get higher and higher. So that means oxygen is getting back into the water more quickly when the water is mixing vigorously and has lots of contact with the air. So this model that we're going to learn today, the Streeter-Phelps model, what it actually predicts is not directly the direct oxygen concentration, but it predicts the deficit, the difference between how much should be there in saturation and how much actually is in the water as a result of those two factors that we're modeling. We're modeling how quickly the bacteria use the oxygen and how quickly the oxygen gets back into the river. So here it is, kind of a complicated equation. What it's saying is that the deficit at a particular time, T is the main variable that we're looking at here, at some time after we mixed the bacteria together with the oxygen and the food, those are the three main ingredients to get a reaction, the bacteria, the oxygen, and the food. The deficit at a certain time can be predicted based on the rate constants that we've already been talking about, the deoxygenation and reoxygenation rate constants. And then also L0, which is the how much BOD is in solution to begin with. Now the second part of the term is if there's a deficit even before you mix the water together. The way that we're going to apply this usually is that we're going to have a stream and waste is coming into the stream. So here's wastewater and here's a river, and so it's flowing this way. So we'll call the river stream 1, the wastewater is stream 2, and then after they mix we'd call stream 3. The way that we're using this most often is to try and find out, as we go down the river, what is the dissolved oxygen concentration. We want to know how it's changing as a function of time or position. And so even before you get moving down the river, it's possible that there could be a deficit. You know, maybe there was some other factory or waste upstream that caused some deficit away from saturation even before it's mixed. But then the condition is going to get even worse as the bacteria begin to break down the BOD as we move further from the mix point. Now the worst case scenario, there's an equation that can find the lowest point in this sag curve. This is called a sag curve because the line sags down and then it starts to go back up again. The point that we're most worried about is what is going to happen to the fish that are in the vicinity of where the dissolved oxygen gets the lowest, or we want to maximize the deficit. And so you can see here it's calling that location D sub C, the critical deficit. And there's a formula that allows us to find out how long it takes to get to the critical time, and then we can take this T that we solve for at the critical time and put it back in the equation for deficit, and so we'd solve for the critical deficit, the largest difference between the saturation and the actual dissolved oxygen concentration. And so we would, here where it says T, what we'd do is we'd find Tc, the critical time, and then substitute it into this formula, and that would tell us the largest D that we're going to see. So the formula that we've just seen here for D, this is solving for how far it is from the saturation concentration down to this sag curve as a function of time. On the vertical axis, we can measure dissolved oxygen, and deficit is a measure of how much dissolved oxygen is missing. And then on the horizontal axis is time, or if we wanted to multiply by the velocity of the river, we can have on the x-axis be distance, how far downstream until we see the dissolved oxygen of a certain concentration. Mm-hmm.
Let's say we had oxygen as a chemical.
Okay.
Like equivalent to the wastewater.
Yeah.
That's also a problem.
That's a really good idea. And sometimes they do that. So he's asking, what if we artificially add oxygen to try and help prevent the problem from happening? And sometimes wastewater does have to be reoxygenated before it's put into the stream. And in fact, that's one of the main points of wastewater treatment is, we know that if we put in too much oxygen demand, it could kill fish downstream. And so what they'll do is they want to remove the BOD from the wastewater, and it's with this model, these equations, you can tell the wastewater treatment plant how much BOD they need to remove. Because you say, well, down here, after it mixes, maybe at the lowest point, we only want there to be 2 milligrams per liter that was taken out. And so you can do all of the calculations, the mixing calculations, and you can do the Streeter-Phelps calculations. If you know that you want this to be only 2 milligrams per liter maximum, then that allows you to tell this treatment plant how much BOD they can have in their wastewater. Like, what's their limit? And then another thing that they can do to help prevent the problem is they can bubble oxygen in their wastewater before they mix it with the river. So that's a good idea you had. That's actually what they do. Now, here's our river that we're going to use for the in-class exercise. All right? It's a beautiful river. I don't remember where this photo was taken. Let's say that we have this river and we know its characteristics. It has a flow rate of 3 cubic meters per second. The temperature is relatively cold. So 5 degrees Celsius is the water temperature. L0, that's how much BOD is in the water just before we add in our wastewater. So upstream, before it mixes, there's some BOD. And then the dissolved oxygen concentration, we measured it before any mixing, we measured it at 7 milligrams per liter. Now, there's already a deficit there because we can go to a table I've shown you before here, and the water temperature of the river is 5, right? So at 5, it should have 12.75 milligrams per liter. If it's in equilibrium with the atmosphere, it should have 12.75. And so the simple fact that it's telling us the dissolved oxygen in this river is only 7 tells us that what we don't see is upstream there must have been some other waste that was discharged already. And so we have an initial deficit even before anything else is mixed. But unfortunately, there is going to be more mixed. Let's say we have a company, Pollution Trading Enterprises, and what they're doing is they're discharging a wastewater. Here's what we know about their wastewater. The flow rate, liters per minute. The temperature, it's a relatively warm wastewater, has an initial ultimate demand of 50 milligrams per liter of BOD, and then the dissolved oxygen of the water is quite low, 1.1 milligrams per liter. So what we want to do is, we know after it mixes, this is the cross-sectional area after it mixes, and we have some rate constants there. We're going to step through the process of applying both the critical and the time to critical, and then what is the deficit in dissolved oxygen. And so let me hand out the papers here. Like I mentioned just a minute ago, I think we may have to double up on some of these. So in that case, if you're sharing a paper with another student, write both of the names on it. And what I'm going to do is I'm going to post the solution to this online immediately after class. And so the fact that you had to share, that's not going to penalize you or anything. But so I'll hand these out until they run out, and then you'll just have to find partners to work with on this. And I'm really going to knock some heads together and find out why they can't put more toner in the copy machine. so we don't have this problem in the future. Who knows? Maybe we'll have enough if enough students didn't come to class today. There we go. So I've asked the questions in a certain order. I try and, hey, we got enough. All right. Okay, so I ask these questions in order of the way that you need to solve them. Rather than just telling you, these are the two things I want you to do, I'm telling you first, find the temperature of the mixed water, then find the mixture, dissolved oxygen concentration, and so on. The first couple of problems are mixed problems.
Usually the wastewater is not treated before it enters the
No, it is. It is treated. Yeah.
then why they don't like adjust the temperature?
It's very hard. It's very hard to get rid of excess temperature. So maybe they did. It's possible that that's the temperature even after they've tried cleaning things up a bit. All right, remember what we do for mixing things? For example, if we wanted to say Q1 plus Q2 equals Q3, when we have two streams mixing together. So here's 2, here's 1, and there's 3. All right. What did we do when we were talking about concentrations? When we had C1, C2, and C3. How did we find the concentration of stream 3? All right, so you multiplied together and then you divided. It was C1, Q1 plus C2, Q2 equals C3, Q3. And so whatever we wanted to find, we'd sort of isolate the variable, right? You're going to do the same thing for temperature, dissolved oxygen, and BOD. Parts 1, 2, and 3 is mixing in the same way that this is. All right? So even though you have your own paper, feel free to collaborate with others as you work on this. Let's take a look at where things are at. Let's just like an intermediate peek at the solution to make sure we're all on the same track. All right. Okay, so I converted the flow rate into cubic meters per second. You have to do that or else it won't work. Okay, so you find the temperature of the mixture. Now if you ever take thermodynamics, they'll tell you that actually this isn't right, that temperature isn't conserved. Heat is conserved, but not temperature. And so, fine, it would be pretty close to this. Like if we were doing it the full thermodynamics way, it would still be closest to 10 degrees Celsius than it would be to any one of the other saturation temperatures. So, any questions on how we find T3? Now this saturation DO, we got that by going to the back of the table here and see for 10 degrees Celsius, it's 11.27 milligrams per liter. So we just went to the table based on that temperature. All right? Okay, we used the same methodology for part 2. The dissolved oxygen times flow rate plus dissolved oxygen times flow rate divided by the combined flow rate, and you get the DO of part 3. Okay? Okay, so I'm going to turn you loose on that. I just wanted to confirm, in case you're getting the numbers so far, that you're on the right track. Okay, so I've just put the BOD concentration of the mixed water on the screen and the initial deficit after they mix. So the initial deficit and then the BOD after they mixed. Is what 10.1? Part 5? All right. Any questions on parts 1 through 4? I mean, this is all mixing and then learning the terminology so far. Learning what we mean by the difference between deficit and dissolved oxygen concentration. The initial deficit is right after they mix, the BOD after it mixes, and so on. So here in part 5, you're basically just substituting in the values that you found earlier through your mixing into the formula. The difference in the K values comes pretty often, and remember the K values have units of days, and so when we find T, the reason why T will have units of days is because that was the K value had inverse days, and it was down in the denominator here in the function. And it's a beautiful coincidence. It's exactly 1/4 of a day. Okay, so we substituted in the initial deficit of 5.17 milligrams per liter. We put in the initial BOD demand of 8.47 milligrams per liter. Everything else is just K values. All right. Any questions on part 5? All right, we're running low on time, so let me show you the rest of the solution here. 0.25 days is how long it takes to flow to that critical point, which is 6.7 kilometers. If you know the velocity and the time, you just multiply them together and find the distance. So 6.7 kilometers, that's the place we need to be the most worried about. That's where the lowest dissolved oxygen is going to be. After that, the dissolved oxygen is going to be going back up again. But this critical point is 6.7 kilometers from where the wastewater comes in. Okay, part 7 and 8 is substituting into the formula for D. So the magnitude of the deficit is 5.24 milligrams per liter. That's how far below saturation it will be at the location we're worried about. It'll be 5.24 milligrams per liter lower than it ought to be. So saturation, we're assuming that it hasn't heated up or cooled down at all as the water has been flowing, and that's an okay assumption. In a quarter of a day, water temperature changes very slowly in the environment, so it's not so bad to assume that the constant temperature has been the case. So our saturation, if it was fully loaded with oxygen, it would be 11.27. We know from the Streeter-Phelps model it's 5.24 milligrams per liter below saturation, and so the actual concentration is the difference between the two. You'll follow the same process when we do the homework problem. I'll give that to you on Tuesday. So on your way out, please leave the in-class exercise on the chair, and there's a number of homework assignments and quizzes that you can still collect on the table. See you Tuesday.